From the studios of Postscript Media and Canary Media.
I'm Shayle Kann, and this is Catalyst.
N2O has a global warming potential around 275, 300 times more than CO2. That's on a 100-year time frame.
Well, the time is finally here when we talk about why laughing gas is one of the biggest problems on the planet.
Catalyst is brought to you by The Antenna Group, the OGs of climate tech PR and marketing. For 25 years, Antenna Group has partnered with category-leading energy transition and clean economy innovators to build their brands, amplify their stories, and market and accelerate business growth. As climate tech moves from the age of innovation to the age of adoption, the stakes are different now, and they're a lot bigger. And there's never been a better time for your brand to leave its mark. If you're a startup, an investor, enterprise, or innovation ecosystem that's creating positive change, Antenna Group is ready to power your impact. Visit antennagroup.com to learn more. Catalyst is brought to you by Energy Hub. Are you ready to use your skills to fight climate change? Energy Hub empowers utilities and their customers to create a clean, distributed energy future, and they are hiring for multiple engineering and client-facing roles. Energy Hub's platform lets consumers turn their smart thermostats, EVs, batteries, and other products into virtual power plants that keep the grid stable and enable higher penetration of solar and wind. All positions can be fully remote or based out of Energy Hub's Brooklyn, New York, or Burlington, Vermont office. Check out open roles at energyhub.com/catalyst. Catalyst is brought to you by Sealed. The Inflation Reduction Act has created an amazing opportunity to transform the efficiency and electrification market, but estimating energy savings is an imperfect science at best. At Sealed, they take the measured approach. With over a decade of experience getting paid based on real energy reductions, Sealed knows that measuring savings is the most accountable, accessible, and simplest way to scale the market for energy efficiency. Visit sealed.com/measured savings to learn more.
I'm Shayle Kann. I invest in revolutionary climate technologies at Energy Impact Partners. Welcome. Well, I've been teasing this one for a while. You may remember that, a month or two ago, we did an episode focused on methane and how it's the most important, least appreciated contributor to climate change. Well, right behind methane is an even less appreciated greenhouse gas, nitrous oxide. N2O, which is also known as laughing gas, is the third largest greenhouse gas in terms of impact on radiative forcing behind CO2 and methane. It has a global warming potential of 273 times that of CO2 on a 100-year basis. And unlike methane, it's actually long-lived in the atmosphere. Not only that, but emissions have been rising. They're up close to 30% over the last 4 decades. And yet, I find at least that we don't talk that much about it. We often don't measure it. And I'm not sure we actually have a really clear view on what's going to drive it to zero. We've talked before on this pod about ammonia fertilizer, but we focused historically on its production and the emissions associated with its production. On balance, the production of ammonia is actually a significantly smaller contributor to climate change than what happens once you use that ammonia as a fertilizer and apply it to soil. So let's talk nitrous oxide. For this one, I brought on Eric Davidson, the N2O guru. He's a professor at the University of Maryland Center for Environmental Science, and he's the principal scientist at Spark Climate Solutions. By the way, you'll have probably picked up by now that I'm a bit obsessed by N2O at the moment. So if you are an entrepreneur and you have a deep tech solution to N2O mitigation, please do get in touch. And as always, you can leave us a voicemail at 919-808-5832. We've had a bunch of really good ones coming in lately. You can also email us at catalyst@postscriptaudio.com, tag us on Twitter, find us wherever you want to. But for now, without any further ado, here's Eric. Eric, welcome to Catalyst.
Oh, thank you. I'm pleased to be here.
I cannot tell you how excited I am to finally do an episode on nitrous oxide. If you have been listening at all, I've been teasing it for months, and only because it took us a while to get this scheduled, and I've just been waiting to get it done. So I'm very excited to have you here because you have schooled me offline about nitrous oxide, and I'm excited for you to reschool me online. Let's start with the basics. So tell me about nitrous oxide as a greenhouse gas. How potent is it? How long does it last in the atmosphere? Like, what are the things we need to know as we start to talk about N2O in the context of climate change?
Okay. Well, first of all, N2O is considered the third most important anthropogenic greenhouse gas, or greenhouse gas produced by humans. CO2 being the most important, methane second, and N2O third. N2O has a global warming potential around 275, 300 times more than CO2. That's on a 100-year time frame. And actually, it's very similar on shorter time frames because CO2 and N2O have similar estimated mean residence times in the atmosphere, although CO2 is difficult to calculate because it exchanges with the ocean and the biosphere more. But anyway, N2O estimated mean residence time in the atmosphere is around 110 years. Estimates have varied over the years depending on who's doing them and the methodologies, but somewhere a little over 100 years mean residence time in the atmosphere. So it's a long-lived greenhouse gas.
And how much of it do we emit? And I mean, you said it's the third most important behind CO2 and methane. Just contextualize it. How important is it relative to those two?
Okay, well, about 7% of the radiative forcing is on the 100-year time scale is attributed to N2O. Then I should also add, though, in addition to its effect on radiative forcing or on global warming, it's also a ozone depleting substance. The ozone is the good ozone and up and high in the stratosphere that protects us from ultraviolet radiation. And N2O is one of the reactants that destroys that ozone. And now that we've been successful through the Montreal Protocol in reducing emissions of chlorofluorocarbons and now hydrofluorocarbons, N2O remains as the largest currently emitted ozone depleting substance. So it really is kind of a double whammy in terms of its impact on atmospheric processes, both as a heat-trapping gas that contributes to radiative forcing or global warming, and a reactant in destruction of stratospheric ozone.
Okay, and then what has the trend line been? So it's 7% of anthropogenic, or of radiative forcing rather. Today, has that trend line over the course of decades and since the Industrial Revolution, has that been growing as a share of radiative forcing? Is it flat? Is it declining? Just where are we on the trajectory of N2O emissions relative to the trajectory we're on with CO2 and CH4?
Well, N2O emissions are going up at an increasingly rapid rate. So the atmospheric N2O prior to the Industrial Revolution was around 270 parts per billion. That's a B as in boy. And it's now up around 335. So it's gone up by about 25%, and it's going up more rapidly in the last decade than the decade before and the decade before that. So it's now increasing at about a rate of 1 part per billion per year. Whereas if we look at CO2, CO2 is still going up, but there's some signs of it starting to, the rate of increase has gone down in certain years. It blipped back up recently, but there's some reason to see that the CO2 trend could be leveling off, and we could even imagine with efforts to mitigate CO2 that it's going to eventually level off and the rate of increase will start to decrease. Methane is much more complicated because we actually had a period where methane leveled off for a while and we weren't really sure why. And now it's gone back up again and we aren't really sure why. So methane's a little more complicated to say what the trajectory is. But N2O is pretty clear cut. It's going up and it's going up faster and faster with every succeeding year.
I don't know if you have these numbers handy, but I'm curious in some of the longer term modeling then what the estimates are, maybe in a baseline scenario of what the proportion of radiative forcing N2O could represent in 2030, 2040, 2050 might be. If it's 7% today, could it be as CO2 starts to level off and decline, who knows what happens with methane, could N2O end up being 10%, 15% of radiative forcing? Is that a realistic scenario, or is it hard to imagine it representing that big a share?
Well, it certainly could go up if CO2 levels off and N2O does not. I don't really have the estimates offhand as to what the upper limit of that would be, but yeah, and of course, the CO2 in the atmosphere will continue being a strong radiative forcer until we actually bring CO2 concentrations down, which is probably going to be many decades off. But in any case, N2O is concerning because it has such a long lifetime that what we're emitting now is going to stay in the atmosphere for 100 years or more. And so, it's going to have an impact on several future generations.
Yeah, in some ways, it's kind of the worst of both worlds between CO2 and methane, where it's like way more potent than CO2 as methane is. It's in fact more potent than methane is even. And it has a long residence time as CO2 does, but methane does not. So it's particularly concerning. This is part of what has me sort of obsessed with it. I guess the final question, just in level setting for you, you've been citing numbers around how much N2O emissions we have and so on. How good have we been about measuring N2O emissions? How much do we know? And how much of a blind spot do we still have?
Well, we're very good at measuring concentrations. That we know is happening. It's going up, and we have, for the last several decades, have had pretty good measurements of it. Going back in time, we can estimate N2O concentrations back in time by looking at what's captured in bubbles frozen in ice cores from Greenland and Antarctica. But that's concentration. You were asking about emissions. And I'd have to say that, well, we more or less know the outlines of the N2O budget in terms of where the major sources are and the minor sources are and what the major sinks and minor sinks are. But there's a good deal of uncertainty in each one of those individual estimates.
Okay, that's a great segue. Let's talk about what we know about the sources and sinks for N2O, and then we can talk a little bit about the uncertainty around them as we do. So just walk me through, I guess, first maybe starting historically, pre-industrial revolution. What was the N2O cycle like, such as it was? And then how have we, as I often say when we're talking about this stuff, how have we messed it up as humans since the 1800s?
Right. So for most of the Holocene, in other words, since the last glacial maximum, N2O in the atmosphere was relatively constant. It bounced around a little bit up and down here and there, but it's been relatively constant until about the beginning of the Industrial Revolution. And the sources before the Industrial Revolution added up to, we think, somewhere around 10, 11, or 12 teragrams of N2O nitrogen. Now, a teragram is 10 to the 12th grams, or sometimes it's also referred to as a million metric tons. I don't think we should get too hung up with the units. It's a lot. But let's just say it's 11 plus or minus 1, okay? And most of that came from, and continues to come from, tropical forest soils. We know that those are an important source. There's also a significant source from the ocean. Pre-industrially, there was a little bit coming from biomass burning. Humans have been burning savannas and using fire to manage systems for a long time. And when you burn vegetation, the vegetation has some nitrogen in it, and a little small fraction of that gets converted to N2O. So there was a little bit of an anthropogenic source prior to Industrial Revolution, also a little bit from agriculture. And they all added up to around 11 plus or minus 1.
Before we move on to what happened in the Industrial Revolution, because we're going to talk a lot more about agriculture and agricultural soils as a source of N2O emissions. But in that tropical forest soil context, before humans were doing organized agriculture, can you just describe the mechanism? What's happening in those tropical forest soils that causes N2O emissions in the atmosphere?
Well, the N2O is produced by bacteria that live in the soil. And there are two different groups called nitrifying bacteria and denitrifying bacteria. And actually, if you want to get real technical, there's also a group of organisms we call archaea, nitrifying archaea. But anyway, these are all microorganisms that live in the soil. And the reason that they do so well in tropical soils is, first of all, it's warm and moist, which makes good conditions for these processes of nitrification and denitrification. And the other thing that's kind of unique about most lowland tropical forests is that nitrogen is an element that's relatively abundant compared to other limiting factors like phosphorus. And that's because those native tropical forests have a significant amount of this process we call nitrogen fixation, which is another set of organisms that pull nitrogen gas out of the air and turn it into a form that the plants can use. It's usually in a symbiotic association with the microorganism in the plant. And so they take nitrogen out of the air, put it into a form that living things can use. And then that cycles through the ecosystem. The trees use it to make their leaves. The leaves fall onto the soil. The roots turn over in the soil, and that adds nitrogen to the soil. And some of these bacteria, nitrifying and denitrifying bacteria, can use that. And in the process of using it, they convert a small fraction of it to N2O. So it's because these tropical forests are very productive and have a lot of nitrogen cycling through them that they are natural sources of nitrous oxide. You can also measure it in temperate and boreal forests, but at a much lower rate because they aren't as productive and don't have as much nitrogen cycling through them.
Okay, so we're going to come back to nitrogen fixation as we talk about the post-industrial revolution. But I want to go back on track. So 11 plus or minus 1 in pre-industrial world, mostly from tropical soils, but some from the ocean, a little bit of anthropogenic emissions. Now take us through the brief arc of history since then and what humans have done.
But before I do that, just one more point about the pre-industrial condition is that the amount that was produced by those sources, say the 11 plus or minus 1, is roughly what is consumed in the atmosphere. So N2O is broken down in the atmosphere very slowly. It's there on a mean residence of 100 and some odd years, but eventually it breaks down in the stratosphere. But the sources and the sink in the atmosphere were roughly in equilibrium. And so the concentration stayed pretty constant over time. As I said, it bounced around a little bit, but more or less constant. Along comes the Industrial Revolution, and that equilibrium is thrown off whack. And for a number of reasons. First of all, with the Industrial Revolution, we started using oil and gas and coal. And when that's burned, there is a little bit of N2O that's produced. Also, we started expanding agriculture. And initially, when agriculture was being expanded, they weren't using synthetic fertilizers then, but they did enrich the soil as best they could with manures, with some importing nitrate deposits from Chile and other places, and also planting nitrogen-fixing crops such as soybeans and peanuts and alfalfa. And so as there were more and more humans needing more and more food, as the population increased following the Industrial Revolution, we started producing a little bit more N2O from our agriculture as well. And then something really important happened along about World War I, and that is that German scientists and engineers invented a process named after the two of them called Haber-Bosch. And that's a process by which they figured out how you could take nitrogen and hydrogen gas and put them together under high pressure and high temperature, and you create ammonia. And from that, then they use that to create nitrate, and they use the nitrate to create munitions. And the reason they were doing this around World War I was that the Germans were fearful that the superior British Navy would prevent them from being able to get to the nitrate deposits that are particularly rich in Chile. And so they needed another source of nitrate to make their munitions. And they succeeded in producing it. Well, for a few more decades after that, not much happened. But then after World War II, we started using the Haber-Bosch process that was being used for munitions now to use to make synthetic fertilizers. And farmers began using synthetic fertilizers after World War II, and the rate of increase just sort of skyrocketed after that. And that was sort of the beginning of the end of an equilibrium of the N2O budget, because once we started using much more synthetic fertilizers, the N2O emissions from agriculture started increasing significantly, and they're still going up.
Catalyst is brought to you by Antenna Group. Antenna Group is the largest integrated marketing and public relations agency dedicated to the energy transition and clean economy. It represents a portfolio of over 75 category-leading companies across solar, storage, smart grid, EVs, electrification, carbon capture, sustainable materials, decarbonization, and beyond. They've been at it for 25 years before clean tech was even a word. They've built some of the largest brands in the industry along the way. With unmatched domain expertise and global teams led by industry insiders, Antenna Group is on the front lines helping climate tech companies with go-to-market strategy, public relations, digital marketing, and much more. If your company is looking to win the hearts of investors, customers, influencers, or strategic partners, look no further than Antenna Group. These guys are also hiring like crazy, so for all you climate communications warriors out there, go to antennagroup.com to check out job openings or to work with them on your PR strategy. Catalyst is brought to you by Energy Hub. Are you ready to put your skills and your passion to work fighting climate change? Well, Energy Hub is hiring 40-plus engineering and client-facing roles that can be fully remote or based out of Brooklyn, New York, or Burlington, Vermont. The company works with over 60 utilities across North America to manage nearly 1 million distributed energy resources like smart thermostats, EVs, batteries, water heaters, and more. In 2022, Energy Hub worked with client utilities and their customers to manage 1.3 gigawatts of flexibility. To put that in perspective, that's nearly a third more capacity than an average-sized nuclear plant. Fighting climate change is a growth industry. Join a team that shares your commitment to a zero-carbon future at energyhub.com/catalyst. Catalyst is brought to you by Sealed, the experts in home weatherization and electrification upgrades, ensuring more comfort for less energy. At Sealed, they know that the future of energy efficiency is measured. The market can be transformed by the Inflation Reduction Act, but only if we move beyond estimates and measure what matters, prioritizing accountability, accessibility, and simplicity in the process. But with this new opportunity comes challenges. Sealed is leading the way with over a decade of experience being accountable to homeowners because they only get paid based on actual energy reductions. Visit sealed.com/measured savings to learn more.
So we were pre-industrial revolution, we were at 11 plus or minus 1 and at equilibrium, more or less. Where are we today? And can you just sort of high level break down the proportion of the emissions today according to the major categories that you just described?
Right. So beyond that 11 plus or minus 1, we're adding another 7 plus or minus 1. All right. And so now we're up to, say, around 18. And of the additional 7 that we're adding, about 4 of that is coming from agriculture. So 2/3, a little less than 2/3. And the other is coming, there's some from industrial processes, there's some still from energy production, there's still a little bit from biomass burning, also some from sewage treatment. And all of those minor sources add up to the other 1/3. But the major contributor is agriculture.
Okay, so let's spend more time on agriculture then. Obviously, that is the biggest component. And you talked about the main mechanism, which is we use the Haber-Bosch process to fix to take nitrogen from the atmosphere. I mean, people don't always appreciate that our atmosphere is 72% nitrogen or something like that. So we basically use this process, combine it with hydrogen, make NH4, which is ammonia, and then either apply the ammonia as fertilizer or turn it into other things that are like ammonia derivatives and then apply it as fertilizer. How does doing that create nitrous oxide emissions? Like, what's, again, the mechanism between we apply fertilizer to fields and then all of a sudden we increase nitrous oxide emissions in the atmosphere?
Right. So the reason we apply the fertilizer to the fields is we want the crops to take up that fertilizer and the crop to grow better and to produce more corn or rice or wheat or vegetables, whatever we're growing. But they're not 100% efficient. You know, they take up, on average, roughly half of the fertilizer that we apply. Some crops take up more than half, some crops take up less than half, but a good rule of thumb on average is that only about half of the fertilizers we put on the land and cropland gets taken up and used to produce the product, the thing that we harvest, the grain that we harvest from the cropland. Some of it is taken up by the plant and it remains in leaves and roots that are left on the site. But a large fraction of it is there and isn't used by the plant. And so these same microorganisms that I was telling you about in the tropical forest also live in the cropland soil. And so if there's nitrogen left over that the plant isn't taking up, they can convert that. The nitrifiers convert the ammonium to nitrate. The denitrifiers convert the nitrate to dinitrogen gas. But in both of those processes, a little bit of N2O leaks out. So we can think of it kind of like a leaky pipe. You're putting nitrogen fertilizer in one end of the pipe and you're taking a crop out of the other end of the pipe, but it's got a bunch of leaky holes. And one of those holes is leaking out nitrous oxide. And there's some other things that leak out too, like nitrate gets washed out into the local streams and groundwater, and that can wreak havoc downstream and cause algal blooms and so forth. But that's not what we're talking about today. But it's similar in that the nitrogen cycle is just inherently leaky. And we can try to get more and more of the nitrogen into the crop and less leaked out, but we're always going to have some leaks. And so unfortunately, the food production system is a system that is sort of predetermined to produce N2O. And what we have to do is try to figure out how to make it more efficient.
So one point that I want to drive home here that I think I've at least heard people getting a little confused about. So there's a big focus these days on green hydrogen, and one of the big areas of interest for green hydrogen is to use green hydrogen in the Haber-Bosch process to make ammonia that is decarbonized in its production. And I think that's important, and that, you know, the production of ammonia is like 1.5% of global greenhouse gas emissions on its own. But it's important to remember that the production of ammonia is actually a smaller proportion of radiative forcing, or it creates a smaller portion of radiative forcing than the application of ammonia on fields, which causes N2O emissions. And so you can make green ammonia, but you solve that side of the equation. You have not done anything to solve the other side of the equation, which is what happens when you apply the ammonia and you get the leaky pipes, as you were just describing. So it's not to say you shouldn't make green ammonia. It's to say there are two separate challenges with regard to fertilizer. One is its production, the other is its application. The application one actually, just in grand total, is a bigger number.
Right. The only thing I'd say about that is that the green ammonia does give you a few more options on how to apply fertilizer, how and when and what form. So if you make green ammonia using renewable energy to produce the hydrogen to make the green ammonia, that presumably could be decentralized. Now, we don't really know what that technology is going to look like, how big those plants are going to have to be. But there are some folks that are suggesting, well, it could be more decentralized, smaller plants, maybe even on the farm scale. And one of the things that farmers in the U.S. worry about is when can they get their fertilizer? Many of them will hire companies to come and deliver their fertilizer in the fall because that's when it's available. And it's also time when they have time to work on it. And it's also time that the fields are a little bit drier. But if they knew they had a more reliable source of their fertilizer that they could get in the spring as their crop is beginning to grow, and maybe even throughout the summer as they might apply additional doses, that gives them some other options of applying just the right amount at just the right time.
Why would receiving fertilizer at the right time contribute to mitigating N2O emissions?
Putting the fertilizer on the cropland at the right time is extremely important because remember, we want the fertilizer to go into the crop. And the more that goes in, that's taken up by the crop plants, the less that's left over to be converted to N2O by these bacteria in the soil. And if you put the fertilizer on in the fall, it sits there all winter long. There's no plants growing unless there happens to be a cover crop. So some places there's plants, but there are not as many cover crops as we'd like. So in many places, it just sits there all winter long. And even though the temperatures are kind of low, still the bacteria are kind of working away at it. And then it warms up in the spring, and you've got all this available nitrogen that those bacteria can use. And the crop is still, maybe it's been planted, but it's just tiny little seedlings, right? And they're not taking up that much nitrogen. And so the bacteria are having a heyday there in that they don't have much competition for it. But if you could wait and put smaller doses on later in the spring and in the early summer as the crop is maturing, now you have a better chance that the crop is going to get the fertilizer instead of the bacteria. Now, of course, there are drawbacks to that. It's easier said than done because every time you put them on, that every application costs the farmer more time and money. But in theory, having that fertilizer available at different times of the year gives you another tool to make its use more efficient.
All right, so we've jumped straight into the next topic, which is how can we mitigate N2O emissions? So green Haber-Bosch or green ammonia production, and sort of optimized application timing as a result of potentially decentralization. That's one, but let's step back. I mean, there's sort of one, I think, broader category, which is just, as you said, the biggest component here is just the leaky pipes of fertilizer application. That's bad for everybody because if you're the farmer, you're spending money on fertilizer. Fertilizer is a huge portion of your operational cost, and your margins are slim, generally speaking. And so you want to apply as little as possible, basically, and you want it to be as much uptake of that fertilizer as possible. The leaky pipes represent loss to you as well. So it's one of these things where it seems like everybody is incentivized to solve this problem as best we can and reduce the leakiness of the pipes. We'll talk a little bit, I think, about some of the more esoteric sort of disruptive approaches, but just in terms of practice, agricultural practice, what are the things that we know farmers can do to both increase their yield with minimal fertilizer application and in the process reduce N2O emissions?
Well, first of all, we have to think of the way the farmer does. And you're right that the farmer is very concerned about costs, and fertilizers, especially nowadays, fertilizers are expensive. The price has gone up in the last couple of years with the war in Ukraine in particular. And so that is a significant concern of the farmer. On the other hand, the farmer also wants to make sure that in a year when the weather is really good, you have warmth at the right time, you have rain at the right time, you don't have too much rain, you want to make sure that those good years you have a bumper crop. And so you want to make sure that there are enough nutrients on the site to be able to take advantage of the conditions in the best years. Now, that may only happen, let's say, 1 out of 5 years. And the other 4 out of 5 years, you've put on enough fertilizer to get that bumper crop, but you don't get the bumper crop. And so you've put on a little bit more than you need for that year, but you don't know which year is going to be which year is going to be the bumper year and which one isn't. So you put that much fertilizer on every year, and it reduces your risk that you're going to miss that bumper year, which can be really important to the bottom line of the farm in the long term. So yeah, economics is important, but also reducing risk is important as well. And so the farmer has to think, well, that additional amount that I spend on fertilizers, yeah, it's significant, but it's relatively speaking, it's not that bad of a deal as an insurance policy to make sure that I get the best possible yield I can. So, yeah, it's important, but there are a lot of factors that go into farmer decision making. So then, to get back to your other question, what else can the farmer do to kind of close up the leaks in the pipe? Well, we've already talked about one, and that is applying it at the right time. And so this is sort of in the context of what many of your listeners may have heard of called the 4 R's, which is what is being promoted, especially in the United States, by both the public sector, USDA, state agricultural agencies, also private consulting firms, and the fertilizer industry is promoting this idea of applying the right type of fertilizer, the right time, the right amount, and the right place. And so that's going to differ depending on what kind of soil type you have, what your climate is, what kind of crop you're growing. But if you can try to understand those things and figure out the right combination of those 4 R's, then you're likely to improve the efficiency by which the crop takes up the nitrogen and less of it goes off as either nitrate into the streams or N2O into the atmosphere. You'll notice that there isn't a 5th R, which would be the right regulation. In the U.S., we have not gone the direction of regulating farmers' use of fertilizer very much. There are a few exceptions. And so the industry is trying to push this 4 R's largely to try to show that they can do this without regulation. Now, if you compare that to Europe, there are certainly cases of legislative initiatives in various countries in Europe and the European Union that are more regulatory. But in the U.S., it's more of a voluntary approach of trying to incrementally improve efficiency through application of these 4 R's. And some of the things that are done to do that are things I already mentioned. Cover crops help soak up some of the excess nutrients so the bacteria don't get them. Minimizing tillage can be helpful. And there are a number of approaches that we call precision farming to try to figure out exactly how much the crop needs and apply only the amount that the crop needs, get a better estimate of what that is. And so these are all technological incremental approaches to try to improve that efficiency.
I know it's going to be very situation specific, but maybe at a high level, do we have a sense of, let's just say farmer X implements the sort of optimal version of the 4 R's, how much of an N2O reduction could we expect? Like you said, are they incremental? Like this is in aggregate a, 10 or 20% impact on N2O emissions, or could they represent a significant mitigation lever?
Well, the nice thing is that extra little bit final increment of fertilizer that the farmer may put on as an insurance policy is the part that's most likely to be lost. And so if we can pull back just a little bit on the amount of fertilizer the farmer thinks that he needs, then we can actually have a proportionally larger impact on reducing N2O emissions. So that's a good thing. As to how low could it go, I've seen some modeling studies that suggest you could reduce N2O emissions maybe by half. But as you said, it's very site specific and situation specific, and so I'd be reluctant to push that number forward very strongly. But yeah, there could be some very significant reductions, and in fact, if we look, when I used the word incremental, I was thinking more on sort of on the national scale. In the last few decades, in the U.S., for example, nitrous oxide emissions from agriculture have been sort of flat. They've maybe gone up a little bit in the last few years, but they haven't gone up much. And that's because we are making some improvements in efficiencies. We're producing more food with about the same amount of fertilizer and about the same amount of N2O emissions. But on the other hand, the N2O emissions aren't going down. So, yeah, it's good news that we're being a little bit more efficient, producing more food for the same amount of pollution, but the amount of pollution isn't going down.
Okay, so let's talk, I guess, for a minute about the more disruptive approaches or the things that are less about practice change and more about technology introduction. We talked already about the prospects of decentralized fertilizer production via Green-Haber-Bosch or some other mechanism. What else is out there that might be, less incremental, more disruptive, but maybe is earlier in the technology maturity life cycle?
Right. There are quite a few, but I'll just focus on two that I've learned from some of my colleagues. One is that to recognize that the vast majority of the crops that we grow are fed directly to livestock. A very small fraction of the crops that we grow are consumed directly by humans. So we're putting a lot of fertilizer on the ground to produce corn and soybeans and other crops that we feed to animals. And of course, the animals are another leaky pipe. The animals excrete a lot of that nitrogen in their urine and feces. And we recycle some of that back onto the land, but our system is currently not set up very well to recycle a lot of it. For instance, we have huge hog operations in North Carolina that's a long ways away from where we grow the corn and soybeans in Iowa and Illinois. So we don't do a really good job of recycling the manure. So that's another place where more nitrous oxide is produced. So what could we do about that? Well, there's a possibility of short-circuiting that supply chain of nitrogen in that we could feed the livestock nitrogen directly instead of having to grow it as a crop. So there are feed additives of ammonia and other nitrogen components. Nitrate can be added to the feed. And there's experimentation with that feed additives. And there's a possibility of also producing synthetic amino acids. And so you essentially eliminate one of those leaky pipes. You produce the nitrogen to feed directly to animals instead of putting it on the ground and hoping half of it gets to the crop and then some of the crop gets to the animals. So that would be one big transformational change. And also improving the management of the feed to the animals could make them healthier animals and could make it more productive for the animal production system.
Theoretically also, just to get like another step more abstract here, you also, if you do that at scale, right, we use a lot of otherwise productive land to produce crops to feed to animals. This is where you've seen like all this deforestation, for example, in the Amazon. A lot of that goes toward ultimately cropland to feed to livestock. And so if you can reduce the cropland that needs to be used to feed to livestock, then you can reforest those areas or avoid deforestation. There's like a bunch of knock-on benefits to that as well.
Right. And we've just barely begun to explore what the impact of that would be in terms of being able to reduce total area of cropland or convert some of that cropland to other productive uses or other productive agricultural uses. So there's a number of possibilities there. The other one is a new emphasis on crop breeding with nitrogen allocation in the crop in mind and the longevity of the crop throughout the growing season. So crops that could grow, that are more cold tolerant, that could grow into part of the winter, would be present to take up those nutrients so that they aren't used by the bacteria that produce the nitrous oxide. Also, if the crops are no longer being grown as much to feed livestock, we don't need as much nitrogen in some of the grain. So depending on what you're using the corn for, some of those uses don't need to have as much nitrogen. And so you could have crops that don't have as much demand for fertilizers. And you could also breed the crops so that more of the nitrogen is retained in the below ground tissues, and so it goes into the soil and gets circulated, recycled in the soil. So taken together, if you do the breeding to sort of change the crop systems, and we've made a lot of progress, in fact, in nitrogen use efficiency through crop breeding, but we could extend that even further through some new efforts in crop breeding. And that, in combination with feeding nitrogen directly to animals instead of via our crop production system, and where you have to use fertilizers in your crop production system to use it from Green, Haber, Bosch, those three things together could be really transformative in the type of agriculture that we have in the future.
All right, Eric, I think we've covered as much of the N2O ground as I had hoped to. This was everything that I had wanted it to be. So thank you so much for coming on and talking nitrous oxide with me.
Well, thank you. It's been a real pleasure. I've enjoyed it.
Eric Davidson is a professor at the University of Maryland Center for Environmental Science and the principal scientist at Spark Climate Solutions. This show is a co-production of Postscript Media and Canary Media. You can head over to canarymedia.com for links to today's topics. And as always, Postscript is supported by Prelude Ventures, a venture capital firm that partners with entrepreneurs to address climate change across a range of sectors, including advanced energy, food and ag, transportation and logistics, advanced materials and manufacturing, and advanced computing. This episode was produced by Daniel Waldorf, mixing by Roy Campanella and Sean Marquand, theme song by Sean Marquand. I'm Shayle Kann, and this is Catalyst.